Okay, these are the notes for 11.4, areas of regular polygons. Now, if you've missed class, you may have missed the exploration we did on this. It is available in Canvas, but we did kind of find all of this by ourselves. We explored where this formula came from. We drew in radii and central angles and apophthegms. So if you have questions about that, let me know, but we did do that the day before we've done these notes. So the center of the regular polygon is the center of the circumscribed circle, and as we did that exploration, you probably saw that. You really had the experience of seeing that circle with the regular polygon. The radius is the distance from the center to a vertex, which is also the radius of that circumscribed circle. The central angle is an angle formed by two radii drawn to consecutive vertices. Consecutive means one and then the one next to it. And again, the central angle here is going to be made of two radii of that circumscribed circle. It's going to be the same idea as the central angle we did in Chapter 9. And the apothem is the perpendicular distance from the center of the polygon to a side. We worked with that in the exploration, so you should have had that experience. And we discovered that the area of a regular polygon is 1/2 the apothem times the perimeter. And then we, in the exploration, worked that out into the area of a circle. This YouTube link here, if you want to see, that kind of uses that idea and shows you another way of looking at the area of a circle, which is where we're going in 11.5. So using your area of a regular polygon, all the ones here are going to be regular polygons. So this is a square. Just to talk to you a little bit about the central angle. Okay, so there's a radii. I'm going to draw in another radii. And think of it this way for a moment. If I draw in these radii, and let's move the apothem for just a second. You can see, remember there was that circle circumscribed about it. That circle would be divided into 4 equal pieces. So to find your central angle, you would take, in this case, 360 and divide it by 4. That's going to make, for a square, not every shape, for a square, this central angle is going to be 90. Well, I also know that radii are equal, so those are congruent. And by ITT, I can say each of these are now 45. And again, this is for the square. It's going to change a little bit for each of the other shapes. Now, when I put that apothem back in, okay, I have 2 congruent triangles. This is a 45, 45, 90. So you can see I have a special right triangle. So what you're going to do is work through this example now that you have that. The radius in the first one is 5√2, so you're going to find the apothem, you're going to find the perimeter, and you're going to find the area of the entire square. And then in the second example, the apothem is √3, and you're going to find all the other pieces. So please work through that and then come back and check your answers. So over here in the green, everywhere you see green is me working through this first row. I had this at 5√2. Using special right triangles, I found the apothem was 5, and this side of that triangle was 5. Since this side is 5, the entire side is 10. So the perimeter is 10 times 4. For the area in the green in this first row, I used 1/2 the apothem multiplied by the perimeter, and I got an area of 100. The blue, all the blue goes together. That's the second row here. Again, the apothem was √3. I used my knowledge of special right triangles to find the radius, which was √6. If this side is √3, the whole side, if the side of the triangle is √3, the whole side of the square is 2√3. So you can see here how I found the perimeter. And then I just did the area a little differently because I know the area of a square is also the side squared. So you can use that here. The answer is 12. I know that looks funny. I'll see if I can fix that. I just wanted to show you that the 1/2 apothem times perimeter formula can work, or the side squared can work. All right, the next one is a regular triangle. And again, find your central angle. So draw a radius in, find your central angle, and then work through the rest of this. I think when you find the central angle, you'll see the special right triangles come through again. So I'd like you to push pause, work through these, and come back for your answers. All right, in this triangle, you can see the central angle was 120. Using ITT, I found each of these was 30. With the apothem, I see a special right triangle. So I found the apothem of 4 by using special right triangles. I found the perimeter here, and the area here. In the blue, again, I worked it out again using what I had. The 2 root 3 came from taking 6 root 3 and dividing it by 3, because that was the perimeter of 3 sides. I divided it by the 3 sides to find each side was 2 root 3. And you can see I used 1/2 the apothem times the perimeter. A popular mistake with triangles is, yes, you can use half the base times the height. Just make sure you understand that the height of this triangle is not 2 apothems. It's an apothem plus a radius, which is a different number than, so like the height of this one would not be 8, it would be 12. It would be 4 plus 8, which is 12. You don't have to use that formula, but that's a common mistake. All right, last one, we have a hexagon. Again, find the central angle. Find the central angle, and you'll see some special right triangles come up. So push pause, work through the examples. All right, over here, you'll see I found the central angle in red. Special right triangles came into play again. The green is working through this example where I have the apothem. The perimeter is multiplying by 6, and I use the area of the 1/2 apothem times perimeter. In the blue, I have that triangle here, and again, using special right triangles and finding the area, I got to here. So if you have any questions or weren't sure about something, please come on in and let me know, and I'll see if I can help you, and you can check the website for the homework.